what we started talking about on Thursday is or on Friday was we started talking about the end behaviors and limits as functions go towards infinity or negative infinity. Meaning, so what we have is we have the limit as x approaches infinity of f of x and the limit as x approaches negative infinity of x. And what we're doing is we're looking as we go farther and farther away from the origin. So as we go farther and farther out to infinity and farther out to negative infinity, where are the y values going? Okay? So we say what is the end behavior of the function? That's what we want to figure out when we're talking about what is the limit as x goes towards infinity or negative infinity. Alright? And what we know is graphically we can connect these limits to infinity or these limits to infinity to the horizontal asymptotes. So we can find the horizontal asymptote of the function. We can say what the limit as it goes to infinity is. Alright? Vice versa. If we can find out what the limit as x goes towards infinity or negative infinity is, we can figure out what the horizontal asymptote is. So we look at this graph right here, these two graphs, and we are looking at what the limit as x approaches infinity is for h of x, and the limit as x approaches negative infinity is for h of x. Alright? And what we're doing here, what we want to figure out is what is this function going, what are the y values of this function going towards as we get further away from the origin. And remember, the origin is right here in the middle. So as we go further and further this way, what y value is this function getting close to? And as we go further towards negative infinity, what y value is this function getting close to? So as you can see, as it goes this way, we're getting close to 2, and as it goes this way, we're getting close to 2. So we know that the limit as x approaches infinity is 2 for both the limit as x approaches infinity and x approaches negative infinity. Right? And what this allows us to say is that our horizontal asymptote is equal to our end behavior, which is equal to minus 2. Right? So because we know our limits are both equal to 2, we know that our horizontal asymptote is equal to 2. And the same thing happens here. Alright? We have this function g of x. We want to find the limit as x approaches infinity and negative infinity. So we can look at this function, and as x approaches infinity, it is further away from the origin, it is approaching this y value. 1. And the same thing if you look at x as x approaches negative infinity, you're approaching 1. Alright? So that allows us to say, again, is our horizontal asymptote is equal to our end behavior, which is minus 1. Alright? And we're not, that's all you have to do if you're looking at the graph. Now, what I want to do here is I just want to look at a couple of these functions right here. Alright? So, again, these are functions that I typically wouldn't expect you guys to know what the graph looks like. Granted, this one we talked about a little bit, so we might have somewhat of an idea. But what we're going to do is when you don't know what the graph looks like, we can minimize this. We can graph it. So we have y equals sine x over x. So you have your calculator, you can follow along here. We have sine x divided by x. So I graph this. Now we're going to talk about this here. Alright. First of all, we kind of already know what we've talked about what this function is going to do. It's going to get, we talked about how as it gets further and further out, it's going to dampen, it's going to get closer and closer, the y value gets closer and closer to 0. So what we can do here, just so we can see one thing, we can go zoom, and we'll do 4 right here. Just so we can see a little bit closer up on the graph. And if we zoom even further out, because so what we want is, we are concerned about as x approaches infinity, x approaches negative. Alright? So if we go look at our window right now, it's our x minimum is negative 4.7. Is that anywhere close to negative 8? No. So let's look at let's make, so let's make that a much smaller number. Let's say negative, say negative 5,000. Let's see what this does. We're just gonna mess with the x value, so let's say the maximum will be 5,000. I mean, those are pretty decent sized numbers. And we're not going to have an x scale of 1 because we don't want 5,000 little, or we don't want 10,000 little tick marks. So we're going to say, we'll make it 1,000. And let's see if this works. Well, we can't see anything because it's getting so close to 0 and our numbers are so big. Alright, so what we need to go over the screen. So just by looking at the graph, we know that as the limit as x approaches positive and negative infinity of this is 0. Alright? Yes. So we said that over here, there's a connection between the end behavior of the function and the horizontal axis. Alright? So if our end behavior for this function is 0, what would our horizontal axis be? 0. So our horizontal axis would be like 0. Alright? Now, also, I'm going to skip this one for now and come down to these ones where we have 3x over the absolute value of x minus 4, just so we can look at this. So what we'll do is again see our graph. Alright, so we're going to graph this where y equals, we have parentheses, 3x plus 1 divided by absolute value, let's go to math, over 1 absolute value of x minus 4. Let's see. We're going to start off with this one, 6. Alright. So, in this graph, so right now we're at 6. So the furthest out we can see is x equals 10. Alright, and x equals negative 10. What we're trying to figure out is, as x approaches infinity, and as x approaches negative infinity, what is the end behavior of this function? So again, we said that, you know, we're concerned about what's happening out at the ends of the graph. Right now, I mean, we're looking at what is the ends of the graph on the graphing calculator, but this isn't anywhere close to what we would want to be working with. All right, we can't really tell what that's going to. So what we want to do is we want to again go to the window, and we'll change our. So we're gonna get a question about your graph. Let me see. So, why don't you hit Zoom 6 real quick? Alright, so that way you can see it. Now, what we're going to do is we're going to change the minimum. We're going to change to the negative 1,000. We're going to change the maximum to positive 1,000. And we'll change the X scale, say, to 500. Alright. So now, if we had looked at Zoom 6, so if here's this still at Zoom 6, if not, what you'll see is when you're at Zoom 6, it looks like your graph is sort of, it's going up here, and it looks like it's approaching as X goes towards negative infinity. It looks like it's approaching like maybe like 6 or so, right? But as you zoom out, all right, and you look further and further out towards negative infinity and positive infinity, what you can see is that this is actually approaching positive or negative 3 as X goes towards negative infinity, and positive 3 as X goes towards positive infinity. All right? And the reason that we want to zoom all the way out is because we're concerned about what's happening at X approaches infinity and as X approaches negative, not as X approaches negative 10 or positive 10, which is what we were looking at more of when we were at Zoom 6. All right, so when you're using a graph to find the limits as X approaches positive or negative infinity, you want to zoom out. You want to look further out than just like negative 10 to 10, which would be Zoom 6. So if you go in and adjust the window, and you have to look at like, put like negative 1,000, 1,000, make your X scale not 1 because you don't want that many little marks. But what we get by zooming out and looking at that is we have it approaches 3 as X gets bigger towards infinity, as X approaches negative infinity, it approaches negative 3. Alright? So, using what we know about the relationship between our behavior and horizontal asymptotes, we could say that the horizontal asymptotes for this function as X approaches infinity is what? What would our horizontal asymptote be for as X approaches infinity? And over here is the right? Now, typically, when you're asked to find the limit as X approaches infinity or negative infinity, it's going to be a little bit simpler than looking at a graph, and we're going to use what we call end behavior models to describe what I'm talking about. All right. So, what we're going to look at right now is end behavior models. Okay. So I want you to write this down. An end behavior model, or we just abbreviated EBM, okay, will give us a graphical description of what the ends of our functions are doing. All right. For instance, if we want to find an EBM for f of x equals x cubed minus 5x squared minus x plus 5, so if we want to find that end behavior model, the end behavior model for this would be f of x equals x cubed. Alright? And the reason that's our end behavior model is because the end behavior model says we only need the highest powered term to determine what the function will be doing as x approaches positive and negative infinity. We only need to look at the term with the highest power. And in this example right here, x cubed minus 5x squared minus x plus 5, x cubed is the highest powered term. So that's our end behavior model. Alright? Now, what this end behavior model allows us to do is it allows us to figure out what does the end behavior of this function look like? What is the limit as x approaches infinity, and what is the limit as x approaches negative infinity? Okay, so looking at this, alright, what we can figure out is that we have the limit as x approaches infinity, so f of x, and the limit as x approaches negative infinity. Alright, we want to figure out what those limits are. So, we're using our end behavior model. Our end behavior model, x cubed, happens to be a parent function that we learned about way back in pre-calculus. And we know what the graph of x cubed looks like just off the top of our head. Alright, the graph of x cubed looks like this. Alright, so since we know this, alright, so the end behavior model looks like this. This is x cubed. That tells us that this function, f of x equals x cubed minus 5x squared minus 5x plus 5, has the exact same end behavior as this function. So if we look at this, as x approaches positive infinity, what is the y value equation? Positive infinity. So this is equal to, and if you look at this as the limit as x approaches negative infinity for this end behavior model, what is the y value approaching? Negative. Alright. So we just found the limits as x goes towards infinity and as x approaches negative infinity for this function f of x without even knowing what that function really looks like. Because we know that its end behavior is the same as x cubed. Okay. And I actually think you guys can remember this as soon as you see how some of this works. Huh? It could. It does negative x cubed. Alright. So what here? That's why it's the most important part of the table. The end behavior model says we only need the highest powered term to determine what the function will be doing as x approaches positive and negative. Alright? We're only concerned about the highest powered term. What is that?
There is. Oh, please.
Alright. Yeah. You ready to rock and roll? Alright. So, what we're going to do now is we're going to look at some examples of end behavior models we're using to find out the limits as x approaches positive and negative. Again, I think that's fairly straightforward. Alright. So, we want to find an end behavior model for each of these three cases. Alright? So, now in these cases, it's a little bit different than what we just looked at because these have numerators and denominators. Alright? But, we're concerned about the highest degree, the highest power in the numerator, and the highest power in the denominator. So, what we can do is we just can, in our minds, cross out anything that's like left over, anything that's what we'll just say is not important. So anything that's not important is any of the terms that are not the highest degree in the numerator and denominator. All right, so this minus 7 is not really all that important when we're trying to figure out the end behavior model. So our end behavior model will be our highest degree term in the numerator and denominator. What are the highest degrees, or what terms do we have in the numerator and denominator at the highest degree? So we have an x cubed and an x to the fourth. So the terms are, so our end behavior model is equal to 3x cubed over 5x to the fourth. All right. Now, in this case, we actually have, all right, the x cubed and the x to the fourth. Some of those x's cancel out. The 3 x's in the top cancel out. So what we're left with is 3 over 5 over x, or 3 over 5x. All right.
Why did it just cancel out?
Because if you look at this, you have 3 times x times x times x divided by 5 times x times x times x times x. So you cancel, I'm left with 3 over 5x. Alright, so now what is my behavior here? Well, this right here is really equal to 3/5 times 1 over x. Alright, and what we can do is, well, we know that the limit as x approaches, okay, so, well, this is all this has to do is find our end behavior model, right? So our end behavior model is this right here, 3 over 5x. Now, we can use that to find out the limit as x approaches negative infinity and positive infinity, all right? Just by looking at our end behavior model. So what we have is the limit as x approaches positive infinity of 3 over 5 times 1 over x. Okay, that's equal to the limit as x approaches. We can use the properties of limits to pull this 3/5 out. So 3/5 times the limit as x approaches infinity of 1 over x. Well, we know that as x approaches infinity for 1 over x, all right, that graph goes like this. All right, and that's horribly wrong, but as x approaches infinity for 1 over x, it goes to 0. So you have 3/5 times 0. So we know that the limit of this function as x approaches infinity would be equal to 0. All right, and we can do the same thing for as x approaches infinity.
What's the graph of that?
That's for, this is the graph of 1 over x. Right. So, and we'll look at some more problems. Now, we have right here, all right? So, we have f of x equals 4x to the 4th plus 7x minus 1 divided by 1 minus 2x to the 4th. All right, we want to find the end behavior model. And so our end behavior model. You guys just wrote down right here in the clearest notes. An end behavior model says we only need the highest powered term to determine what the function will be doing as x approaches positive or negative infinity. So what are the terms up here that have the highest power?
2,
That's 4.
4. Yeah.
4 to the 4th. And what else? What's the highest term that we denominator? 2x to the 4th? or
Oh,
-2x.
negative.
Okay, well, in this case, x to the fourth cancel out. I'm left with 4 divided by -2, which is equal to -2. So that's cool. All right, so I know that the function -2 is just a constant function, so it's going to look like this right here. So what that tells me is that this function, all right, has the limit as x approaches positive or negative infinity of f of x is equal to -2. All right, because I know that my behavior model is the function y equals -2. Now, since the limit as x approaches positive and negative infinity is equal to -2, what am I horizontal asymptote be? -2. So horizontal asymptote would be y equals -2. Okay? Another one. What are the highest terms, or the degrees, what are the terms of the highest degrees here? Human third. Alright. So, again, what terms here, what terms we have as the highest power terms? So we have our end behavior model would be what? Here, go. X2 squared. X squared. Alright, so, anything cancel out here? All of them? Two of them. So we're gonna leave that with good, R 3x. Alright, now, if we look at what the function 3x looks like, okay, you should know what this looks like. It's gonna be something like that. Oh, no, it's not. I just moved something like more like this. Alright, so, as you can see, the limit as x approaches positive infinity here is what? Shamar, say something about it. Positive infinity. So we can say the limit as x approaches positive infinity for f of x is equal to positive infinity. And the limit as x approaches negative infinity is going to be what, Shamar? Negative infinity. All the way down there. Right? So, and the behavior models, that's how they work. So now I think we need to make some generalizations. Alright, so, here we go. Algebraically, and we're going to talk about this now because this should be a refresher from pre-calc way in the beginning. So, when the highest exponent is in the denominator, okay, the limit is always zero. Does that sound familiar? You had rules about horizontal asymptotes. So we said that the degree in the denominator was higher than the degree in the numerator. The limit was y, or the horizontal asymptote was y equals 0. If the degrees were equal, what did we do? Divide what? So divide the coefficients. And then if the degree in the numerator was larger than the degree in the denominator, it was what?
There was none.
There was no horizontal asymptote. What we call an oblique asymptote, which we don't necessarily want to touch. So, just to look at this, so, okay, what is the, so all you have to do is find the NMA remodel, all right? So what is the, well, actually, I'm going to do that. Okay, so what is the highest exponent in the numerator? X cubed, right? That's our highest term is x cubed. What's the highest term in the denominator? X to the fourth. Alright, so the exponent in the denominator is larger than the exponent in the numerator, therefore this limit is what? 0. Done. That's pretty simple. Okay, here we have sine x divided by x squared. Okay, what is the highest degree in the numerator? That's sine x.
X was one.
That's inside the sine.
What is the?
There's no like, well, right? So there's no, the highest exponent is 0. What's the highest exponent? Up. Because when we're looking at this, we aren't looking at that sine, that x, that belongs to sine. That's like, it owns it. Alright? So we don't look at that in terms of its exponent. So the highest exponent in here is 0, the highest exponent down here is 2. Well, 2 is bigger than 0, so the limit of this will be 0. Pretty straightforward, huh? Only your homework is that easy. It was.
I feel like with your teaching, it's not gonna get it home.
No.
Yeah, can you break down?
What? These are the ones on hospitals.
No, it's just one.
We're going to go through each one.
Okay.
So what would the horizontal asymptote be for each one of these? What would the horizontal asymptote be for each one of these? 0. Good. So, next. The highest power is the same in the numerator and the denominator. The limit is divide now. I put leading coefficients. I could just put coefficients because we should know that we're only looking at the highest degrees. All right. Leading coefficient refers to the coefficient in front of the term with the highest degree. Okay. So the limit as x approaches infinity of 2x squared plus 4 divided by 3x squared minus 1. Okay. Well, how do you do that? So we divide the leading coefficients of the highest terms. So x squared and x squared. All right. So we're going to divide the leading coefficients 2/3. So it's 2 divided by 3. What is the horizontal asymptote? 2/3. All right. That's also the horizontal asymptote. All right. What about the limit as x approaches negative infinity of sine x plus x squared divided by 4x squared? 1/4. How do you get that? So the 1 comes from the 1x squared divided by 4 from the 4x squared. Because all we're doing is dividing the leading coefficients. So it's 1/4. Again, also the horizontal asymptote. All right. Okay. Now we got the limit as x approaches infinity of x plus 2 divided by 4x squared minus 1. Slightly more challenging here, huh?
I'm pretty sure you're gonna say that.
Well, I mean, there's just a little bit of stuff here. So if you look at this, all right, so what we can do here is, again, we only care about this in terms of the highest degrees, correct? Good. So what term has the highest degree in the numerator? Where? Yeah, numerator. It's x, right? And what term has the highest degree in the denominator?
I'm not sure about the square root and
Okay, so the 4x squared, we can cross out everything that's not the highest. 4x squared it's the highest degree, right? However, it is the square root of 4x squared. Well, the square root of 4x squared is going to be equal to 2x. Right?
So what was that minus the?
Well, we did minus 1. Another thing is about to. Okay, well, here we go. Here's actually our highest terms right here. So we have a 1x over a 2x, so if we divide the coefficients, our limit would be what? Yeah. We're done. Question on that? Pretty straightforward, huh?
Yeah.
Almost like calculus is easy. Almost in this area. Okay. All right. When the highest power is in the numerator, the limit, all right, is going to be Greek aspect. We are not going to have a horizontal asymptote, right? And we also want to make sure that we also make sure that we know which infinity we're looking at. We're looking at as x approaching infinity, or we're looking at as x approaches negative infinity, right? Again, we're only concerned about which terms.
Oh, is there
Which terms are we concerned about?
the power?
Okay, the terms of the highest powers. So, all this stuff, not really relevant to us. That plus 4 doesn't really affect it. So we have 2x cubed over x. Well, all we have to do here is we can still create an behavior model. So 2x cubed over x simplifies into what? 2x squared over 1 is 2x squared. Alright? Well, we know what that graph looks like. That's a parabola. Alright? So it's going to look something like this. Okay? It looks like our parent function x squared. Alright? We know that function, regardless of which infinity you're going towards, that function approaches positive infinity. So the limit as x approaches positive infinity is equal to positive infinity. Alright? Now we can look at the next problem. It says the limit as x approaches negative infinity of x to the fifth plus 7x plus 4, alright, divided by 3 minus x squared. Again, we're going to look at the highest, or the terms with the highest degree, the highest powers. Alright, so x to the fifth has the highest power here. Alright, the term with the highest power down here is negative x squared. That's going to give me, negative x cubed that function looks like. That function looks like this. Alright, so the limit as x approaches negative infinity would be what? Positive infinity. Again, pretty sure that all you use is the n negative minus 1. Okay? Questions?
Let's not do that anymore. Oh my gosh, what was this? Maybe it's like one. Oh, that hurts so bad.
What?
Okay.
So, what we're going to talk about now is the idea of continuity, which you guys have heard before. Alright? So, if a function is said to be continuous at a point x equals c, right, there is no interruption in the graph at that point. Alright? And mathematically, what that means is, we're in a math class. That means that a function is continuous at x equals c if the limit as x approaches c of f of x is equal to f of c. Alright, so if the limit of f of x is equal to the value of the function at c, then that means that that function is continuous. Alright. So, what that is saying is, put this. Okay. So I have a function with an interval called a to c, where this is important. This right here. The function is continuous at x equals c if the limit as x approaches c of f of x equals f of c. Alright? So this graph I Alright, so what I want you guys to notice is this. Alright, we're looking at this function I just drew. Okay? And in order for this function to be continuous, what must be true is that the limit as x approaches c, so x approaches c right here, so closer and closer on both sides. As the limit approaches c, first of all, that limit must exist. And second of all, that limit must equal the function value of f of c. Alright? So, as we can see, as we approach closer to c, and as we get closer to c right here, alright, that limit is approaching what from the right or the left? It's approaching 4. Well, okay, so what we have is the limit as x approaches c of f of x, so this function right here, that's 4. Because it's approaching from the left at 4, it's approaching the right at 4. So since the left-hand limit and the right-hand limit are equal, the overall limit, that whole limit is equal to 4. Alright? Remember that? Well, the function value is also 4. We look at the function value of C, so f of C is also equal to 4. So since the limit of x approaches C of f of x is equal to 4, and the function value at C is equal to 4, that means that that limit is continuous at x equals C. That makes sense. So with this function that we have here, in order, like, we want to say, okay, we want to prove this function is continuous at x equals C. The only way that can be the case is if the limit as x approaches C of f of x is equal to the function value of, so f of C. Alright? The function value here is you go here, we're looking at C, you go up, you see it's that point right there, go across, so that function value right there is 4. The limit is 4 because the left hand, as you're approaching the left, it's approaching this y value of 4, and as you're approaching the right, it's approaching this y value of 4. Therefore, that whole limit exists as 4. So since the limit is equal to the function value, this function is continuous at x equals C. Now, a more basic way of saying this is if a function is said to be continuous over an interval a to b, the graph can be drawn without picking up your pencil. It is a smooth, unbroken curve. So I can draw this.
You want to write this down?
And it does not have to pick up my pencil. You can simplify this by saying a function over the interval a to b is continuous. If I can draw it out, I think I did that one. Right? That's just an easy way. That's just an easy way to remember that something is continuous. You can draw it out picking up. Okay. Questions about the idea of how? Can someone quickly say out loud how you know if a function is continuous at a certain point?
If the limit of f x approaching C of f of x is equal to x C. Right.
Not as x approaches C.
No, what do you mean? X approaching C. Oh, huge confidence.
Yeah, you can all that stuff there.
Because I've been writing C for the past 3 weeks. You know what my hair looks like?
All right. So here's that. We have functions that are continuous, but functions that aren't continuous have what we call discontinuities. So we have to talk about the 2 types of discontinuities here. Okay? So, first one is a removable discontinuity. Okay? And that means is that we are able to fix the problem by filling in a single point. Alright? So, we are able to fix the problem by filling in a single point. Alright? That's why it's removable, because all you have to do is fill it in. Okay? A non-removable discontinuity, we can't fix the problem. Alright? We can have something like a vertical asymptote. I want to make you write the whole thing. Alright, so it would look like vertical asymptote would look like all kinds of things. That's it. A vertical asymptote. We can also have a jump discontinuity. Alright? And what that's gonna look like is maybe something like this. Okay? And both of these, we cannot fill in, like, you can't fix the problem just by filling in a single point. Alright? In order to fix this jump discontinuity, we would have to move this entire piece of this function down. Remove this entire piece up. Alright? So, this is not just one point that we have to fill in. This over here, well, this is like an infinite hole. Like, you can't, like, if you try to fill in this hole, you're going to sort of dump that, you're going to try and fill it in, and when you fill it in with it, it's just going to keep, still all that space underneath it, and it doesn't actually fill up. You can't fill up an infinite, like gap. Alright? So, questions about that? Now, there are some different classifications of these discontinuities. Alright, a hole. Alright, a hole is really our only fittable discontinuity.
You only read this in our color.
Not really that big.
Okay,
A hole is just where you have a function, and
are these all non-removable?
well, first of all, these are all in your book, so if you don't want to write it down, it is in your book. Alright? You have a hole.
Well, okay, and it's non-removable.
A hole is a removable discontinuity. Okay? Because I can fill this one single point in with some value, and it now continues. All I have to do is say, okay, I'm gonna let this function equal that point right there, and now that's a continuous function. It's filled up. I can just draw that without having that, have to worry about that, like, not being defined. Okay? This would be a removable. We kind of talked about jumps and infinite discontinuities. Alright? Infinite discontinuities are going to be your vertical asymptotes. They are not fillable. Okay? You cannot, they are non-removable. Jumps are also non-removable because we said you can't just fix it by filling in one single point. You have to move like the entire piece of the function. Right, so I'm not going to redraw those just because we just did draw those, right? Right? And then an oscillating function, that's from the experience that I've had so far, you will probably not have to deal with that much, but what that looks like is I'm not really good at drawing this. So for what instance, one oscillating function would be y equals sine over 1x. Alright? Now what this looks like, okay, is first of all, there is going to be a vertical asymptote at x equals 0. Alright? But this function is going to come and go like this. It's going to go. And it's just going to keep, I'm going to stop it, it's just going to keep going. And then it's going to also be coming over on this side too. Alright? So what's happening here is this oscillating function. Alright? You can't figure out what is actually, well, you can. What's happening here is, as it's getting closer and closer to x equals 0, it just keeps going up and down, up and down, up and down, up and down, up and down. Alright? So, I mean, this is really the only time that you might see an oscillating discontinuity. Most of the problems that we deal with won't have that. Alright? So, going over to this. Yes. Right? Algebraically, how do we find points of discontinuity? Well, yeah. Yeah, yeah, yeah. I know. That you guys have done this. Alright, algebraically, how do you find points of discontinuity? Well, we're gonna be looking for, we're gonna look for, parts of the domain where it's undefined. So we're looking for where is a function undefined. Alright, typically that's gonna happen when you have rational functions like this, or where you have square roots. So most of these are going to create poles, vertical asymptotes, possibly jump discontinuities if you're working with piecewise functions. All right, so we are going to look at a few of these. All right, so for each function, we're going to find all the points of discontinuities and tell if they are removable or not removable. So you have f of x equals x divided by x squared minus 1. Okay? First of all, if I see x's in everything, that's telling me that I can probably cancel out x's. Alright? So, what I see is, I'm going to have, okay. So, where would this function be defined, or undefined? If we have a numerator and denominator, where would this function be undefined? Nope. The denominator, because the denominator cannot be what? Huh? Now you're thinking about n behavior and whatnot. I'm asking you, what can the denominator of a fraction not be? There's no problem here about it. It definitely cannot be this.
Okay, so I'm saying. I'll just tell it.
0. Because you cannot divide by 0. So x squared minus x cannot equal 0. Well, right here I can factor this into x times x minus 1, which cannot equal 0. So x cannot equal 0, and x minus 1 cannot equal 0. This turns out to tell me that x cannot equal 1. Alright? Now, I need to figure well, this is basic last year. So, the denominator cannot be 0, because if it was, it'd be something divided by 0. Okay. So, what I did is I said x squared minus x can't equal 0. I factored an x out of both of these. So I get x times x minus 1 cannot equal 0. X can't be 0 and x minus 1 can't be 0 because if I'm multiplying two numbers, one of them has to be 0 in order for this to equal 0. So I know that this can't be 0 because x cannot equal 0, x minus 1 cannot equal 0. X cannot equal 1. That's not as simple as it gets. I don't think. Can't really break it down too much work.
So in essence, x cannot equal 1.
That's going to find the points of discontinuity. Alright? Now, when it says find all points of discontinuity, we're concerned about only the x values. Alright, so right now what we have is our points of discontinuity are x equals 0 and x equals 1. So x equals 1 and x equals 0 are our discontinuities. Now we need to know which type they are. Okay? So we need to know if they are removable or not removable. So the only time we're going to have a removable discontinuity is if it is a whole. okay? And the whole is only gonna happen when the numerator and denominator both equal 0. So if I plug 0, if I plug 1 in, I get 1 divided by 1 minus 1, which is 1 divided by 0. Does the numerator equal 0?
No.
No. That means that, so since only one of them equals 0, which is the denominator, this is non-removable.
Next equal 1 is?
Yes. The only time you're going to have a removable, or a removable discontinuity, when you have a hole, and that's going, well, yeah, when you have a hole, and in this case, that's going to be when both the numerator and denominator equal 0. I plug 0 and I get 0 divided by 0 minus 0, which is 0 divided by 0. So this is a removable discontinuity. This is a hole. Okay?
So it's a whole when the numerator equals 0.
It's a hole in both the numerator and denominator equal 0. All right. This one right here. All right. 1 divided by x squared plus 1. All right. All right, so when would this be undefined? What would we need to look at? We need to look at the denominator. The denominator cannot be equal to what?
0.
So x squared plus 1 cannot equal 0. Subtract 1. X squared cannot equal negative 1. That's good because x squared will never equal negative 1. So, in fact, what we find here is that this function is actually continuous. Because x squared cannot equal negative 1. Right? That's perfect because no matter what number I square, it's never going to equal negative 1. Right? Because I have negative 4 squared is 16. Negative 1, that's 1. Right? It's never going to equal negative 1. So this is actually a continuous function. How do I know that? Because the only place this function is going to be not continuous is where this denominator equals 0. This denominator never is going to equal 0. Okay? Now, we will look at 1 minus 2x, or y equals 1 minus 2x where x is less than 1, and y equals x squared where x is greater than or equal to 1. Alright? So, what we're going to do here is we're going to evaluate both of these. So this is the left-hand side, right? Because if you think about it, we're going to have, so what we really have here is you have 1 minus 2x, which would be graphically something like this. 1 Alright, so actually it's going to be, yeah, we're not necessarily going to graph this every time. So this function is going to look something like that, and then we have x squared, and then evaluate that. If I put 1 in here, 1 squared is going to be 1, which is going to be right there, and I do 2, that would be 4. So this function is going to be like that. Alright? Graphing it, you can see that this is what type of discontinuity. What? jump discontinuity, which is removable or non-removable. Non-removable. We know this is a non-removable discontinuity, but we don't want to have to graph it every time. So how can we do this out of grade?
Okay, where's the hole? What is that?
This is 1, -1. That's not, technically, that's not, that's a place where the function is not defined. It's not a hole, it's a jump discontinuity. So, how do we tell if this is a jump discontinuity or a hole or something? You know, how do we know that without actually having to graph it? Because we don't want to have to graph it. Well, what we can do is we plug this in. All right? Because we talked about limits back in the day of these types of piecewise functions. And what we're going to do to see if the limits are to see if they're going to the same place, we're going to plug in the one on the left-hand side and the one on the right-hand side. If they're equal, that means that they are. That would mean that it's a well, that would mean that it would be not a jump. All right, if they're equal. So not equal, that means it is a jump discontinuity. So if we take this, we have 1 minus 2x, which would be 1. 1 minus 2 would be -1. So on this side, we get -1, which, as you can see in our graph, and on this side, we get y equals 1. Okay. Those are different numbers. Okay? If they're different numbers, then it's going to be a jump discontinuity. Okay? Typically, you're going to see these piecewise functions are going to have mostly jump discontinuities. Now, every once in a while, you can see it have where it might be equal. So if this said y equals 1, this said y equals 1, it would be continuous. All right? As long as one of these said, if this said less than, that say greater than, it would turn out to be a whole. All right? How's this seem right now? I guess we'll see it in the homework come. So let's see if we can calculate what else. Bypass this now. I don't use a good calculator that I have up right now. So, well, I'm not going to. What about writing an extended function?